PI 510, Pressure Vessel Inspection Code, Chapter 5. In Chapter 5, we already discussed inspection, examination, and pressure testing practices in the previous module. Here we just go quickly through the preparatory work prior to inspection. Apart from lighting and scaffolding, there are some safety measures to take, the question or ask normally in the exam. And some of the safety measures are draining, cleaning the vessel, purging with some inert gas, and then gas testing to ensure that there is no harmful gases inside the vessel. Otherwise, if it's not possible, then breathing apparatus should be used. Ordering of the area, removing irrelevant personnel from the area to minimize the risk, posting warning signs, having an attendant at the entry to the vessel to watch the inspector in case he needs help or anything, and also warn others that the inspector is working inside the vessel, isolating tank inlets by blinding off the inlet and outlet nozzle, checking of safety equipment and inspection tools to ensure that they are in good working order. For development of an inspection plan that is normally prepared by inspector and or engineer, pressure vessel engineer, a corrosion specialist may be consulted to identify the potential damage mechanism. So proper NDE techniques or methods can be selected to capture those expected damage mechanism, the result of those damage mechanism, which are discontinuities. Inspection plan includes identifying the inspection location, that's normally done by the inspector, or the condition monitoring location, CML, and determining the inspection interval based on the corrosion rate or rate of damage growth. Previous inspection reports and the equipment repair history are obviously important source of information. Other tools that are used are management of change, MOC, that should be documented and approved, the changes in the process fluid and operating condition. Risk-based inspection assessment, which is basically focusing the inspection activities on critical parts and equipment, dismissing less beneficial inspections. RBI assessment is achieved through calculating the probability and consequence of failure for each scenario. For example, it makes sense to direct the inspection efforts such as profile radiography for available thickness on pressure containing parts than the less important components such as drainage. Inspection plan shall include identifying the type of expected damage and the most vulnerable locations. This information helps selecting the type of NDE that can detect the expected damage of the minimum critical size, and also identifying inspection monitoring location based on most vulnerable locations. According to the fracture mechanics philosophy, all materials contain cracks. However, these little cracks are not detrimental to the integrity of material equipment until they reach a certain critical size. So as long as we keep an eye on them and they are below their critical size, we are safe. Similarly, the critical size of discontinuity depends on type of material, that is how big the discontinuity a specific material can tolerate, which in turn depends on the mechanical characteristic of the material, the tensile strength and the toughness specifically, and amount of applied stress, since any discontinuity is inherently a stress riser. Minimum contents of an inspection plan. Identify type of inspection. Is it external, on service, in service, or internal, and their interval. Identify inspection schedule or timing. Identify any preparatory requirements such as cleaning, gas testing, scaffolding, lighting, access, tools. Refer to the inspection procedure and inspection report template for how to do each inspection and how to record them. Refer to Acceptance criteria or applicable codes for evaluation of test results describe the relationship between various disciplines and their responsibilities: engineering, operation, maintenance, QA, QC. In case of alteration or a change in integrity operating window, the original design input or output is changed, and hence engineer's approval is necessary. So remember that for alteration, engineer's approval is necessary. If both the engineer and the inspector, if the operating temperature or operating pressure of the vessel is changed, this means a change in IOW, and hence the engineer needs to recalculate the design using existing metal thickness in order to determine whether the vessel can still withstand the new IOW safely or not. The same is true when the replacement material is changed, because it is no more a like-for-like replacement. So it's not a simple repair. Risk-based inspection, RBI. Risk-based inspection is aimed at directing inspection efforts to those areas where a high risk of failure or leak is expected. RBI helps eliminating or reducing inspection efforts from areas where risk failure is low or when there is no significant consequence in terms of equipment operation and safety, while using those resources to improve inspection efforts where a high risk and or consequence of failure exists. The primary purpose of RBI is inspection plan, and a byproduct of RBI can be more efficient use of inspection, and it could be a saving in inspection, although that's not the purpose of RBI, but you could save on inspection cost. The risk of failure is determined by two parameters: probability, which is the likelihood, and consequences. Probability of failure means what are the chances. POF can be determined through design output, how wide the safety factors are, operational condition, any upset and their frequency, equipment condition, age, maintenance records, quality of inspection and maintenance plan, prevailing damage mechanism, type of process fluid, past inspection report, and experience gained from the past failures. Consequence of failure means what happens if the fluid is leaked or the vessel fails in this case, because leaking means failure according to RBI. Loss of production, it could be explosion, it could be fire, and it could be even loss of life. How much of fluid would be released in case of a leak or failure, and what effects it would have on the vessel, environment, and living creature. RBI assessment includes type and location of damage, probability and consequence of failure, type and interval of inspection, type and percentage of NDT or coverage, whether pressure tests required after the repair to validate the design and vessel performance, and if any preventive or mitigating measures recommended. RBI shall be documented in order to understand the underlying reason for type of inspection selected and their interval determined, NDE technique selected and its coverage, any repair or replacement recommended. Preventive measures such as process fluid change or use of inhibitors may also be recommended. These are called non-inspection recommendation. Frequency of RBI assessments. RBI shall be reviewed after any inspection, repair, or change of process fluid to understand whether the assumption made earlier are still valid, or RBI assessment shall be revised based on new information and parameters introduced. The half-life can be determined by RBI to be over 10 years, but RBI reassessment should be done after 10 years or when the initial assumptions have changed. For example, when the process fluid is changed, because API 510 says the maximum interval is half-life or 10 years, whichever is less. But with RBI, you can have a Next inspection interval more than 10 years, provided a reassessment is done after 10 years, each 10 years. Preparation for inspection. Safety. Gas test to ensure there are no harmful gases before entering the vessel. The vessel should also be isolated so there is no ingress of fluid or gases from connections or inlets. Suitable personal protective equipment, PPE, such as hard hat, safety boot, goggles, masks, earplugs, gloves, breathing apparatus. Boiler suit should be available or coverall. Also, proper lighting, scaffolding, access, warning signs have been put up and the area has been cordoned off in order to keep non-relevant personnel at a safe distance. Permit to work is issued and valid. During pressure test, visually inspect the vessel for leaks and distortion when the pressure is reduced from the design pressure to maximum allowable working pressure. That is the hydro test pressure divided by 1.3 times at ambient temperature, or pneumatic test pressure divided by 1.1 at ambient temperature. So remember that when you do the visual test, you bring down the pressure to maximum allowable working pressure. That's for safety reason. Equipment. Assess if there is sufficient light outside of the vessel, access to vessel is available, ladder and scaffolding, electrical equipment are de-energized, NDE and repair equipment are safe and appropriate. For example, tools should be spark-proof for H2S solar service environment. Ensure there is sufficient light inside the vessel for inspection, NDT examination and repair. Ensure the vessel is clean enough so that possible expected surface defects are not obscured during inspection. Communication. Prior to inspection or repair, permit to work need to be obtained and relevant personnel shall be informed of the type of work being carried out inside and outside of the vessel. It might be a cold work permit or hot work permit. It's always a good practice to carry a toolbox meeting in presence of all relevant personnel to go through the safety measure, ensure risks are determined or mitigated or eliminated, and unavoidable risks are understood by all relevant personnel. During vessel entry, safety assessments such as gas tests need to be carried out. Vessels shall be properly isolated and de-energized, turned off and locked down. Confined space entry procedure shall be followed. Proper PPE worn. All hazards shall be identified and removed or mitigated to as low as reasonably possible. Alarm. So this could be an exam question what alarm means, as low as reasonably possible. And the risk are further reduced by using proper PPE. Remember, when it's mandatory to wear a personal protective equipment PPE, it is a clear indication that certain risks do exist that could not be completely eliminated during the design, construction, repair, or alteration stage. So wearing a PPE is actually a sign of danger. You shouldn't feel comfortable and safe when you are wearing PPE. It's just mitigating risk. Record review. Before the inspectors enter the vessel, he or she shall review previous inspection reports, repair reports, and any engineering assessment, as well as inspection reports from other vessels with similar service conditions. This would help the inspector to understand what type of damage might be expected. API 571 damage mechanism that we brought on Module 6 and API 579 Fitness for Service, FFS, provide good guidance and recommendations. Inspection for different types of damage mechanism and failure modes. There are various types of damage mechanism ranging from mechanical damage such as fatigue and creep, environmental damage, salt, moisture, temperature, process damage, erosion, corrosion, or combination of them, sulfide stress corrosion. The relevant damage mechanism damage profile and NDE techniques for damage detection shall be discussed in Module 7, 571, RP damage mechanism affecting fixed equipment refining industry. You may also appreciate the fact that in a particular damage mechanism is directly related to the material of construction. The primary goal of internal inspection is to find damages that cannot be found otherwise by external or on-stream inspection, such as inspection of internal linings and internals such as trays. During internal inspection, internals and linings need not be removed unless they show damages such as bulging and crack, or when you suspect damages underneath that you need to remove the internals to the range of damage or the extent of the damage. Internals are removed for inspecting underneath or for getting access if required. Although the internal inspection is the most costly and intrusive type of inspection, but it is also the most comprehensive one. Very useful and cost-effective inspection can be performed by NDE examiner under inspector supervision and approval, using an approved NDE procedure. Thickness measurement is part of the NDE on-stream inspection. NDE technique is chosen based on their capability to detect the expected damage. Please note that there is always an inherent limitation for on-stream inspection, such as access, inability to examine internals, and internal lining. On-stream inspection. Please note that on-stream inspection is done in view of internal inspection only when internal inspection is not practical for such reasons as access limitation. Visual inspection of vessel from outside to detect any bulging, sagging, out of roundness, corrosion, distortion, leakage from weep holes. External inspection. Insulation need not to be removed for inspection unless there is evidence of corrosion under insulation, such as leak, bulging, change of color or visible stain, localized hardness, dimple, and the like. On-stream inspection can substitute internal inspection when the vessel has a corrosion rate of less than 0.005 inch per year and remaining life of more than 10 years. So the calculated remaining life should be more than 10 years, and the corrosion rate should not be more than 0.005 inch. Then you can use on-stream inspection and substitute it with internal inspection, provided it gives you almost a similar information that you get with internal inspection, or it is not possible to enter the vessel due to size or any other reason. If substituted for internal inspection, the on-stream inspection and the outcome of it shall be equivalent to internal inspection. So it should give you the same information. Thickness measurement is an important element of inspection. For general corrosion, localized UT thickness measurement is carried out and compared with previous data in order to identify the critical areas and also to determine the remaining thickness. Remaining thickness is used to calculate the remaining life of the vessel and the next inspection interval. The inspection points are selected by the inspector based on the most probable areas of damage and corrosion. These inspection points are called conditioning monitoring location, CML. Subsequent thickness measurement or NDE examination shall be taken from the same CMLs to allow comparison. So obviously you need to take the same measurements that it was taken in the last inspection interval so that you can compare the loss of the wall thinning or the loss of thickness due to corrosion during the inspection interval, so you can compare them and determine and calculate the annual corrosion rate and the future inspection interval. For localized corrosion mechanism, profile radiography or UT scanning is used to understand the distribution and population of damage and the pattern of material loss. So for localized corrosion inspection, UT spot thickness check is not good enough. It might not give you a true representation of that. So for that, you have to do UT scanning or profile radiography. The inspector shall compare the results with expected calculated corrosion rate. In case of significant discrepancy, corrosion specialist is consulted to help understand the root cause and recommend remedial actions such as re-rating, using inhibitor, changing process fluid, retiring the vessel, revisiting inspection interval, using alternative NDT technique. Corrosion under insulation. The vessel may be insulated externally for process reasons such as maintaining a uniform temperature. Although insulation protects the metal from external corrosion, but it could also backfire. That is, if a corrosion starts under the insulation for any reasons such as breakage in protection and leak, the rate of corrosion would be faster than when metal was not insulated, because the insulation itself would increase the local humidity and temperature, the accelerators for corrosion. Below, you can see the temperature range at which corrosion may occur for carbon, stainless, and duplex steel. As you have noticed, carbon and low alloy steel are most vulnerable than stainless steel, because as you can see, the temperature range is wider. So at a wider temperature range, it is vulnerable. And the stainless steel does 140 to 350, while carbon steel does 10 to 350. So it's a lower range, so it's less vulnerable. And lastly, duplex is 280 to 350. So in a very narrow range, it is vulnerable. So it's the least affected by corrosion under insulation. The most visible corrosion and under insulation damages are sagged, caulked, or cracked insulation. So the visible CUI, this could be a potential exam question, whether it's sagged, caulked, or cracked. Look for areas where there is abrupt change of shape on the vessel, such as nozzle, manways, water traps, under pipe supports, and where there are penetrations such as stiffening rings, ladder connections to vessel, etc. Remove part or all of the insulation if telltale signs indicate possible abnormal corrosion such as temperature difference or leakage. Otherwise, it's not necessary to remove the insulation. That is, an external inspection should suffice. As you can see here, caulking, and here you see there is a sudden change of shape here, direction. So these are the areas that are most vulnerable to corrosion under insulation. And for temperature difference, you can use infrared or backscatter neutron technique that tell you the temperature difference between various parts of the insulation. So that can be a telltale sign of the corrosion happening there under insulation. Operator surveillance. In case of any unusual condition observed by operators, such as vibration, leak, noise, any damage to insulation and corrosion, they are required to notify the inspector for further investigation. Condition monitoring location. In order to monitor vessel's corrosion, we need to identify several locations on the vessel and measure their thickness periodically. The selected locations shall be representative of vessel corrosion rate and shall be selected where maximum corrosion or other damage mechanisms such as erosion may exist. These locations are typically selected from head, shell, cone, nozzle, upward of bends, etc. The thickness measurement is either done by profile radiography for localized corrosion, pitting, and general corrosion, or UT spot thickness measurement for general corrosion. Sometimes an electromagnetic scanning is performed to find any anomalies, which then helps us to zoom in, examining that area at a closer angle and therefore locate the most deteriorated area. Several UT thickness measurements are carried out within those zones to determine the metal loss and the remaining wall thickness. The measurements could be point measurement or an average of several measurements within an area. Previous inspection reports are a very good tool to locate the previous inspection, examination, and measurement location, and also compare current measurements with previous ones in order to determine the short and long-term corrosion rates. Corrosion and process specialists could also be consulted to locate the most vulnerable areas which have a higher potential for corrosion. Number of CMLs or condition monitoring location depends on the type of fluid, consequence, and probability of failure or the risk, or when the corrosion is general and not localized. So if it is localized, you have to increase. If it is high risk, you have to increase the number of CMLs. Obviously, more critical areas shall have more CML and more frequent inspection. Examination technique selection. Magnetic particle is used for ferromagnetic material having surface cracks or cracks close to surface. Liquid penetrant used on all types of materials having discontinuities and cracks that are on the surface or open to the surface. Radiography is used for materials having internal discontinuities and cracks, and also for measuring the remaining thickness by profile radiography. However, RT is not very accurate for detecting laminations and lack of fusion. Lamination on base metal and lack of fusion of welds. Ultrasonic UT is used for detecting volumetric discontinuities. UT is very good at detecting lamination and lack of fusion, and is also used for thickness measurement, but UT is not reliable for near surface discontinuities. They call it near field, so it's not very good for thin material. Electromagnetic ET is very good for scanning corrosion under coating and also localized loss of thickness. ET sweeping or scanning ability helps identify locations for further examination by more accurate UT thickness measurement. Infrared thermography, IRIS, measures the temperature and is frequently used for corrosion under insulation inspection because temperature increase at a location indicates possible loss of insulation or damage to insulation. Field metallographic replication and metallographic is the only way to detect metallurgical changes or damages that cannot be detected by NDT techniques. Pressure testing. Pressure testing validates the design. It demonstrates that the vessel can withstand the calculated design stress. A successful pressure test demonstrates that the vessel can easily withstand the maximum allowable working pressure without any leakage or distortion. It is analogous to procedure qualification record PQR for validating welding procedure specification, WPS. Hardness test Beaker's Brinell is a quick and cost-effective tool to detect loss of ductility and therefore the toughness. Indirectly, I mean, if the hardness is more, you have an idea that toughness actually is reduced because the ductility is reduced. Please note that you need not be an expert in NDE or a technician in performing NDE examination, but as an API 510 pressure vessel inspector, you should understand how these methods and techniques works, know their advantage and limitation, and be able to review the NDT reports and approve them. And that's why we brought a comprehensive module on NDE as on module 3. The relevant NDT techniques shall be discussed in module 3 as in section 5. Prior to 1999, the pressure test was performed at 1.5 times of maximum allowable working pressure. After 1999, pressure test is taken as 1.3 times of MAWP. This is because of increased quality in manufacturing of pressure vessels on plates. The reason being that with the advancement of technology, better material manufacturing technique and better quality were achieved, and hence a higher factor of safety was no longer necessary. The safety factor was also reduced from 4 to 3.5 after 1999. Subsequently, the pressure test was reduced from 1.5 times of MAWP to 1.3 times of maximum allowable working pressure. Pneumatic test is carried out at 1.1 times of MAWP. The pressure for non-coated vessel is determined by the owner user. Pressure test is not normally required for repair or like-for-like replacement of parts, as the initial design parameters and assumptions are not changed and still valid. However, if the inspector feels that the pressure test is beneficial to demonstrate the capability of vessel to withstand maximum allowable working pressure safely and include the pressure test, he may include the pressure test activity in the inspection plan. Then the pressure test shall be carried out. Pressure test on part or section of the vessel shall be applied in consultation with the engineer. So remember, if you decide to do the pressure test, consult with the engineer as an inspector. Pressure tests are normally required for alteration when initial design parameters are changed. This is to ensure that the vessel is suitable for intended use as well as validating the new design calculations. If the applied pressure is more than their set pressure of valves and gauges, then the pressure relieving devices, such as safety valve, relief valve, pressure and temperature indicators, shall be either removed and the opening blinded, or the relief valve shall be clamped down so that it doesn't give off pressure as an alternative method prior to starting the pressure test. Prior to hydro test, ensure that the supporting structure can withstand the weight of water when the vessel is filled. If not, then the alternative pressure test would be either a pneumatic test or a squeeze test, which is a combined hydro pneumatic containing 50% potable water and 50% inert gas, such as nitrogen. The squeeze test is normally done on pressure vessels installed in offshore installations, where the structure may not withstand large pressure vessels weight when fully filled with water for pressure test purpose. Check the water certificate for potable water. For 300 series stainless steel, the chloride content shall be less than 50 ppm. Inhibitors may be added to prevent any possible corrosion. Carbon steel and low alloy steel are prone to brittle fracture, especially at very high pressure, such as design pressure, which is at least 1.3 times of MAWP and low temperatures. To avoid this problem, API 510 prescribes that the metal temperature should be maintained at least 30 degrees above the MDMT, minimum design metal temperature, for vessels over 2-inch thick, and 10 degrees Fahrenheit above the MDMT for vessels with a thickness of 2-inch or less. This is the only uh, discrepancy between ASME Section 8, construction code for pressure vessels, and API 510. It is more relaxed in API 510. It says over 2-inch, it should be 30 degrees above MDMT, and for less than 2-inch, it should be only 10 degrees above MDMT. Whereas in ASME Section 8, it straight away says it should be 30 degrees above MDMT. It doesn't talk about the thickness. Thickness doesn't matter. But obviously, the thicker material are because of plane strain, and they are more vulnerable to fracture. Please note that the thicker the material, the more the probability of brittle fracture, because the higher would be the temperature gradient across the thickness, and also because of plane strain. The temperature of test fluid should not be more than 120 degrees Fahrenheit. Please note that any fluid, including water, could be used for hydro test as long as the test pressure is below the fluid boiling point and the fluid is not combustible or corrosive. In case both the hydro and pneumatic pressure test is not possible, alternative NDE examination may be performed subject to approval of both the inspector and the engineer, such as they say the gold well. For example, there is a piping offshore. You cannot, that's the last well. They call it gold well because you cannot pressure test the last well when it's connected to the system, a module. So they do intensive NDE, like both UT and RT, to ensure that that weld is good. So that way they validate the whole system. Material verification and traceability. Normally the owner user would require PMI, positive material identification, for exotic material. Opting for PMI may depend on other factors, such as when the consequence of using the wrong material is too high, or there is a suspicion that the material were mixed up. PMI is either done by a spectrographic analyzer or X-ray fluorescence analyzer. And API RP578 is the reference document for PMI. Most of the projects, they use a spectrographic analyzer that because it can detect carbon while X-ray fluorescence cannot. Inspection and repair of flange joints. Flange joints should be inspected for evidence of leakage, drips, stains, gasket sitting, face corrosion, thread engagement, and markings.